Okay, this section is called graph theory. It's completely unrelated to vectors. Cognigy does a pretty good job going through this, but this is just an extra resource if you want. So I'll go through some of the same concepts and examples. So this is called a graph, and the order is something you might be asked for. And it is confusing because we're using some of the same notation. The order is, it looks like this absolute value bar, kind of like vectors. And this is the number of vertices in the graph. So vertices are like A, B, C, D. So the order of this graph would be 4. And the size of the graph, also with the same notation, is defined as the number of edges. So that would be like segments. A, B, and then BD is another edge, AD is another edge, BC, and CD. So altogether, 1, 2, 3, 4, 5. So we'd say the size is 5. So let's look at this one. The order, and you can just write order if you want. The order of this one would be 1, 2, 3, 4, 5, because there's 5 vertices. So it's just getting used to, like, you know what vertices are probably. Just getting used to the new notation. And then the size is essentially, like in geometry, we call these diagonals. So all the diagonals, 2, 3, 4, 5, but then you have to also include the sides, which there's 1, 2, 3, 4, 5. So there's, the size would be 10. Okay, and then we've got degree of a vertex is the number of edges that connect to the vertex. So we could say, like, the degree of A would be equal to 2 because it has 2 edges coming out of it. Okay, and then degree of C would also be 2 because there's 2 coming out of it. But the degree of D would be 1, 2, 3. And also the degree of B would be 1, 2, 3. Degree of B. So that's the degree. So let's kind of go back and do also the size. The size of this one, that would be the number of edges. I think we did this one before. 2, 3, 4, 5. Size is 5. And then the order is 4. 1, 2, 3, 4. Okay, it's easy, but at the same time confusing. Different types of graphs. Simple graphs, multigraphs. The way you can tell a multigraph is because it will have a loop. So like from here, it starts at B and it comes back to B. Or you might have something like these going on in multigraphs. Notice like there's multiple edges between A and D, and then also between B and C. These are called multiple edges, whereas in a simple graph, there's just one edge. And we've seen multigraphs before with probability. So hopefully those look familiar. And then complete graphs is when every vertex is connected to every other vertex. So like this first one is kind of a trivial case, but it does count, and then so on. So as long as every vertex is connected to every single other vertex, it's called complete. Notice this first one, A is not connected to, we're missing AC is not connected, and B is not connected to D. Otherwise, now this one would be complete because all the vertices are connected to each other now. Okay, and then we have something called weighted graphs, and this is these could represent time, distance, cost, just depending on the situation. So one situation they use in the book is like a think of like the U-Bahn map. If these are different stations in a city, and these maybe are the times: 9 minutes, 8 minutes, 3 minutes. So we would ask then, what is the quickest route from I until H? And so there's a lot of different ways to get there. We could go this way from I to L, and then we could go to K, and then we could go to H. So we'd write that I, L, K, H, and add all those up. 9 plus 8 plus 3 is 20. And we want to try to get the shortest route. So then what's another way we could go? We could go down here to S, and then we could jump all the way across to H. So ISH, but that would be 5 plus 17. Okay. It's fewer changes, but it's actually taking longer. And then we also have, how else could we get there? From I to L, and then we could sneak down. We can't stop here, although it looks like maybe this would be a good route to then turn right, but we can't do that. We have to go all the way to N and then back up. So that was I, L, N, H. So that's 9 plus 9 plus 3, and that is 21. Okay. So it looks like that first route was the quickest. Okay, and then we have something called directed graphs, where notice the arrows now, kind of like vectors. This is a graph that has specific directions, and they're called directed edges. So again, kind of like an U-Bahn map, where maybe a track only goes one direction, and you can't turn it around and go a different direction. So this could represent streets, another common example that we'll see. And then we've got these in degree and out degree. So the in degree of vertex is the number of adjacent edges that have a direction into the vertex. Adjacent just means next to, kind of like with trigonometry. The out degree is the number of adjacent edges that have a direction out of the vertex. So we could do a couple examples. What is the in degree of vertex E? So here's vertex E. How many edges are coming into that vertex? We've got this one right here is going in, but then there's 2 going out. So the in degree is only 1, and the out degree is 2 because of these 2. Okay, another one. Maybe I'll just pick a random, maybe A. What's the in degree of A? So that would be 2, because these are both going into 2. So in degree of A. And then we could say, what's the out degree of A? And that would be 0, because there aren't any arrows coming out of A. So another simple kind of counting skill. It's just important to practice these over and over and get used to the vocabulary, because it's not a hard concept. I think you can tell. Okay, and then subgraphs are where you've got a bigger graph like this, and then you're taking smaller parts of the original graph. And so which one of these is actually a subgraph of the original? Like this first one, let's call this A, B, C. Graph A, can you find this graph somewhere over there exactly matching, like with the arrows and everything? I think you can probably see it's this piece, but something's missing. There's no arrows on this. So we wouldn't call that a subgraph. So A is not a subgraph. And then B, if we look, okay, E to D has the same arrow, and D to F has the same arrow. So, but it's missing this little part. But let's come back to this and look at the second one. D has an arrow going to E, which is not the case here. It's the opposite. And D going to F is the same, and then E going to F is the same. But since this is not the same, this can't be a subgraph. This one is technically a subgraph because even though it's missing this part, these other parts are true about the original. So it's kind of this is probably the trickiest thing so far. Trying to figure out what's a subgraph and what's not. Okay. So that's it for graph theory. Like I said, it's a pretty quick, unrelated concept. And now you should go try the quizzes, or you can do all the examples in Cognigy as well. So this section will be used further in the context of other sections too. So thanks for watching. Bye.